Okay, welcome to another video. Today I'm going to walk through the second day of Bayesian statistics workshop. So in this situation we have a random variable that has a binomial distribution with 5 trials and a probability of success p that we don't know. So we're going to use Bayesian statistics to try to say something about p after we end up observing that x came out to be 4. So first question is, what's the likelihood function for p? And to do this is what we've been doing for a while now. So you just take the probability mass function for your probability distribution that you're working with. This is the probability mass function for a binomial distribution. And you take your values that you know. So we know that n is 5 and we know that k is 4, so we're going to substitute those into the formula, and then the only thing we don't know is our parameter p that we're trying to estimate. So we get this likelihood function right here, and it's not so bad. It's 5 times a simple polynomial, p to the 4th minus p to the 5th. Next question is, if we start with a prior distribution where we're completely unsure what p was before we did our experiment, then you could model that by saying p could be anywhere between 0 and 1, all equally likely. So then what you do is you want to know, okay, given that prior distribution, then what's the posterior distribution? And what you do is you multiply prior times posterior, and prior times likelihood, and you get the posterior distribution. In this case, multiplying by this prior, because it's just constant, it's just 1, it doesn't really do anything. So the posterior distribution ends up being the same as the likelihood function, or at least proportional to it. So if it's proportional to it, then we might want to know, like, what's the area underneath the curve so that we can figure out how to scale it so that it actually becomes a probability distribution. So the likelihood function we can integrate. So I just took my likelihood function, 5 times p to the 4th minus p to the 5th, and integrated that. It's easy to integrate. Just raise the powers, divide by the new powers. The constant 5 just waits while you do that. Plug in the bounds, 1 and 0. I got 1/6. So that's the area under the curve. So the likelihood function is not a probability distribution. We've said that before. But we know that when you multiply prior times likelihood and you get this, you know that the posterior distribution, which should be a probability distribution, is going to be proportional to this function that we started with. So this is essentially the posterior distribution, except it's too small because it doesn't have the right integral. The integral should be 1, not 1/6. So we just need to scale it or normalize it. And obviously the way to scale this is to multiply it by 6. And so that's what the question here is to show that the posterior distribution is 30 times p to the 4th times 1 minus p. So it's just 6 times bigger. Why is it 6 times bigger? Well, that's what it needs to be so that it has an area under the curve of 1. And so here's my solution. I just say, okay, we know that the prior is the constant function 1 as long as we're between 0 and 1. And the likelihood is the same as what we just calculated. So multiplying prior times likelihood to get the posterior, we're just getting the likelihood function. And then the rule in Bayesian statistics is that your posterior function is directly proportional to, that's what the symbol means, the prior times the likelihood. So it's directly proportional to that formula, 5 times p to the 4th minus p to the 5th. But that formula is too small to be a probability distribution because the integral is only 1/6. So if we make it 6 times bigger, then this will become a 30, and then the integral will be 1, and it will be a probability distribution. So that's what the posterior distribution is. Notice the notation that I'm using here for posterior distribution. I'm using the Greek letter pi to represent both prior and posterior distribution. The prior is pi without any other details other than the parameter. And then the posterior is pi of p given the observed value of x that we got. So given whatever our sample data was. Okay, the next question was after I did a quick introduction to beta distributions. So this posterior distribution is an example of a beta distribution. Anytime you have your parameter to like an alpha power and then 1 minus the parameter to the beta power, and then the support of that being between 0 and 1, then that's what we call a beta distribution. The constant is whatever it needs to be so that the integral becomes 1. In this case, 30 was the right constant. Beta distributions are really handy when you're doing Bayesian statistics for an unknown proportion. Here are some different example graphs of different beta distributions for different alphas. I've pulled all of these up in Desmos so you can take a look at them. When alpha and beta are both 1, you can see that the beta distribution is just sort of like this simple parabola looking thing, right? The most likely value of p, the unknown p, would be 0.5. It's the highest likelihood. But the integral of this is 1, so it makes a probability distribution. So the area under this parabola is 1. So that's a good example of a beta distribution. Actually, I'm lying to you. This isn't normalized. The area actually is not 1 here. So you can adjust the constant to get it to be whatever height would be the right height. But remember, when you're doing likelihood functions, it doesn't matter what the constant is. Anything that it's proportional to is just as good as anything else. It's only when you need a probability distribution that you need to normalize it so that the integral is 1. Okay, that's when alpha and beta are both equal and small. You get a nice balanced thing like that. The next example, I have an alpha that is 2 and a beta that's 5. And so you can see it's sort of lopsided. You're more likely to have a lower p given that you had more failures probably. So that's why beta is bigger. And so you get this sort of hump at the beginning and then a longer right tail for the beta distribution. And then if you go with an even bigger alpha and beta, again now equal, this is alpha and beta both equal to 10, then you get something that looks more like a bell curve, right? It's a skinny bell curve though, and in fact the bigger alpha and beta get, the skinnier the bell gets. And if they're not equal to each other, then you'll be skewed one way or the other. And if they are equal to each other, then you'll get nice and balanced in the center with 0.5 is your most likely outcome. So that's how the beta distribution changes as the two values of alpha and beta change. Okay, last question was, it says here beta distributions are useful because if you start with a beta prior, then you end up with a beta posterior, which is a really nice property in Bayesian statistics. It makes it really easy to work with these beta distributions. I started with, in the last problem, a uniform prior, which is a really simple prior, but it's not always appropriate because sometimes you actually do have prior knowledge, like you have reason to believe that the parameter p might actually be closer to one number than another number, and you want to use that knowledge to get the tightest estimate on what p actually is. And so a good starting point would be to start with a beta distribution. If you do that and you want to find the posterior distribution, you do the exact same math we just did. Now your likelihood function, if you have an observed value of x that's k and an arbitrary number of trials n, then you can use letters here, but just understand that n and k are constants. It's p that's the unknown parameter, that's the variable. And then you do prior times likelihood. And our prior is this prior, it's the beta prior. It's saying that the prior distribution is some constant, which doesn't really matter, times p to the alpha and 1 minus p to the beta. And then we're going to multiply the prior times this likelihood function. And again, notice I've written the likelihood function as being proportional to this, because again, the constant, the n choose k in front, really doesn't matter, right? You only care about what it's proportional to. So this is what matters. Multiply these two things together, and you get a really simple outcome for the posterior distribution. It's just p to the alpha plus k, and 1 minus p to the alpha plus the n minus k power over here. So that's what you get. And clearly that looks like a beta distribution. It's going to have a constant out in front that'll make the integral equal to 1. Whatever that constant is really doesn't matter. You can integrate this to find out. And it's usually not too hard to integrate these beta things, but you can always use something like Wolfram Alpha to make your life easy if you want to do it on the homework. Okay, that's it. We'll talk a little bit more about how you apply these to real-world problems next time. Let me know if you have any questions.